Fun example. Andy the adventurous adventurer, while running from evil bad guys in an Amazonian rainforest, trips, falls, and slides down a frictionless mudslide of height 20 meters, as depicted here. Once he reaches the bottom of the mudslide, he has the misfortune to fly horizontally off of a 15-meter cliff. So he has gravitational potential energy up here. As he slides down, all of that's going to be converted into kinetic energy, and he's going to be moving completely horizontally, so he'll have a velocity here corresponding to his kinetic energy. And at that point, he becomes a projectile. How far from the base of the cliff does Andy land? Well, let's treat this as two problems. A conservation of energy problem here to find his horizontal velocity, and a review of projectile problems down here to figure out where he lands. All right. First step, let's find what his potential energy due to gravity is up here. That's going to be mgh, and that's going to be equal to his kinetic energy down here, 1/2 mv squared, by conservation of energy. So the height difference is 20 meters. So as we do some of our cancellations, m's cancel out. We can say again that v equals square root of 2gh, or that's going to be square root of 2 times 10 times his height of 20 meters from when he goes over the cliff, or 20 times 10, 200 times 2, 400. Square root of 400 will be 20 meters per second. He's going to fly off the cliff horizontally with the velocity of 20 meters per second. Now we've got a projectile problem. Horizontally, he's going to have a constant velocity of 20 meters per second. If we can find how long he's in the air, we can solve for his displacement horizontally, d or delta x, which is just going to be his velocity times the time. To figure out how long he's in the air, though, we have to look at vertical motion. Vertically, his initial velocity is 0. His final velocity we don't know. Delta y is going to be 15 meters from the time he goes off the mudslide to hitting the ground at the bottom of the cliff. So that's 15 meters. We'll call down the positive y direction again. A, our acceleration, is going to be 10 meters per second squared, down. And let's see if we can solve for time. The equation I would use to do this is I would say that delta y equals v initial times t plus 1/2 at squared. V initial is 0, so that whole term goes away. We could then write that t must be 2 delta y over a square root, or 2 times 15 meters over 10 meters per second squared square root. So t equals, when I plug all that into my calculator, I come up with the time in the air of about 1.73 seconds. And if he's in the air 1.73 seconds vertically, he must be in the air 1.73 seconds horizontally. So d, or delta x, is just going to be velocity times time. Delta x, which is d, will be vt, or that's going to be 20 meters per second times our time of 1.73 seconds. It's going to give him a displacement horizontally of about 34.6 meters. This distance right there must be 34.6 meters from the base of the cliff. Conservation of energy problem combined with our knowledge of projectile motion. Hopefully that gets you a good start with conservation of energy. Thank you for your time and for watching Educator.com.